particular problem we have the problem states that comets travel around the sun in elliptical orbits with large eccentricities. It says if a comet has a speed of 2.0 times 10 to the fourth meters per second at a distance of 2.5 times 10 to the 11th from the sun to the sun, and it wants us to find what is the speed when the comet or comets is at a distance of 5.0 times 10 to the 10th meter. Okay, so here I'm just going to give you a visual. I just found this image. So here's the sun, and because it says elliptical orbit, I just found something that has an elliptical orbit here. So in this case, here is the comet traveling around an elliptical orbit. So I'm just going to go ahead and label stuff in this particular image that I find, just to help you visualize stuff. So the first thing I'm going to label is all this information given to me. Alright, so here I'm just going to go ahead and draw the distance from the sun to where the comet currently is in this particular diagram. I just pick a couple of points, just FYI. You can pick whatever points you want. But here, I'm just going to call this Ri, the initial distance away from the sun, and that is given as 2.5 times 10 to the 11th. And at this particular distance away from the sun, the speed, the tangential speed, is given as 2.0 times 10 to the fourth meters per second. Okay, and it wants us to find the speed when the comet is at a distance of 5.0 times 10 to the 10th. I do want to point out that 10 to the 10th is less than 10 to the 11th. So here, I'm just going to pick a point and draw a line that is a little closer to the sun because it is 5.0 times 10 to the 10th. So here it implies that the second location relative to the sun is closer. So I'm just going to pick that dot there just as a reference point. So I'm going to call that point RF. That's my second location. You can call it V1 and V2 if you want. And then at this location, I'm going to draw my tangential speed just a little longer, only because if you are closer to the sun, you are going to be traveling faster. Your orbital speed is going to be faster because the gravitational attraction is greater. Okay, so here I'm just going to go ahead and set up constant mission angular momentum. This is a planetary system. It implies that the net torque is 0. You're in space, so angular momentum has to be conserved. So I'm just going to go ahead and set up Li equals Lf. L here stands for angular momentum. So I'm just going to go ahead and therefore break this function up into what is defined as. Angular momentum is defined as the moment of inertia of an object times its angular speed, and that equals to the final moment of inertia times its final angular speed. And here, I'm just going to go ahead and break up II into CMR square. The moment of inertia function of a point mass is just CMR square. So here I box CMR squared to point out to you that it is a point mass. Well, if it's a point mass, C is going to be 1. So the value of C for a point mass is going to be 1. So while you see C on both sides of the functions, you see that I'm going to go ahead and cancel it out only because 1, it appears on both sides, 2, it's just 1. So multiplying by 1 is kind of redundant. Okay, so what I did on the left side here, I also did on the right side. I just broke IF into CMRF, and then omega F stays there. But here, I want to go ahead and take it just a step farther. I'm not given what the angular speed is. Rather, I'm given the tangential speed, which is 2.0 times 10 to the fourth meters per second. And then it wants us to find just the speed here when it is at 5.0 times 10 to the 10th. So I'm going to recognize that I don't have omega. Because I don't have omega, I can translate omega into its linear relationship here. So omega is simply V tangential initially divided by how far it is away from the focal, here the focal being the sun. Alright, so I did that on both sides. So as you can see here, M is going to cancel on both sides because it appears on both sides. And then on the left side, this is Ri square. On the bottom though, you have Ri, so I'm going to go ahead and cancel that square with the Ri on the bottom. And likewise on the right side, I have Rf square, and then I have Rf on the bottom, so the square for Rf is going to cancel with the Rf on the bottom. So really, this particular function reduces down to just this particular ratio. Ri times Vi equals Rf times Vf. Well, here I'm given Ri, I know Vi, I know what Rf is. So once again, if you've been keeping up, the problem states, it gives you a lot of information here. So the only thing I don't have is Vf, which I'm asked to find. So how fast is this particular comet or comet system orbiting around this sun? Okay. So here, really, once you're done with the physics here, it's just really plug and chug. Ri is given as 2.5 times 10 to the 11 meters, and then its initial speed at this distance away is given as 2.0 times 10 to the fourth meters per second, and then the second R here, our F in blue here in the diagram is given as 5.0 times 10 to the 10th meters. So I did all that on my calculator and I got 1.5 times 10 to the 5th meters per second. I'm hoping my calculator works on point here as I'm watching the basketball game. So that is my answer. However, I do want to point out that this is a problem that I got from a textbook source. As you can see, it's nicely printed here. However, I got 1.0 times 10 to the 5th meters per second. This is problem 13.65. Except when I went to check to make sure I'm not tripping, again, as I'm watching this particular basketball game here. Hold on, let me see. I did check, and the solution in the back of the textbook here for 13.65, where my cursor is in the middle of your diagram there, it says 6.8 times 10 to the 4th meters per second. So either I'm tripping out or the author is tripping out. Alright, other than that, I want to stick with my answer because that's what my calculator gave me. Alright, stay nerdy, don't be whack.